Hello, everyone. Um, Christopher Himmel. I am going to talk this evening about neural networks. I want to give an introduction uh, and also talk about the basic structure of neural networks. So let's do it. So this is a basic agenda for what we're going to talk about. We're going to first go through the biological motivation behind artificial neural networks. We're talking about neurons and what they're made of. Then we're going to do a mathematical approximation of exactly what we started with, which was that biological breakdown. And then we're going to show this simple perceptron, which was the first time the neuron was modeled, many decades ago, at least half a century ago, and then we're going to build it up from there. We're going to start with a simple neuron, the perceptron, and then we're going to show how that is actually logistic regression when we start to put multiple points together. It could be just one neuron, but multiple inputs. And we're going to show how when we make a more complex neural network, then we can represent this in mathematics with matrices with some linear regression. And also show one part of the neuron, the activation function. We're going to show all the math behind that. So, and then at the very end, we're going to build a neural network from scratch. Start with a single neuron, then we'll make it a layer of neurons. And then we're going to make it multiple layers, which actually is a deep neural network. So that's what we're going to do tonight. So let's start with the neuron structure. Biological, what does a neuron actually look like? And very shortly, you'll understand why I'm showing you this. But yeah, so there's really four major parts to a neuron. Neuron is a cell in the brain, in the nervous system. It's what makes us really smart, is all these neurons. So let's look at the smallest fundamental piece of a neural network of the brain is a neuron. Neuron consists of the cell body, which you can see here. And it basically sends a pulse out. If it gets enough input, it sends a pulse out. So we're going to do that in math shortly. So where does it send a pulse out to? It sends it out through this axon, which this axon is actually where the learning happens. The stronger this axon is, the more of that pulse makes it out of the neuron, out into this area, which then goes through these synapses. And you have to imagine, okay, for a second, another neuron over here. There's other neurons that these synapses are connected to. So they activate the next neuron. And how do they activate it? They activate it through dendrites, which these dendrites are activated from another neuron at this end. You have to imagine more neurons that are sending out their pulse and coming in through, the pulse is going through the axon to the synapse and then into the next neuron through the dendrites. Okay, so that was basically how a neuron looks. Now let's take the same pieces, the cell body, the axon, the synapse, and the dendrite, and let's look at how mathematically we would represent that. So the axon is coming from other neurons, and the axon is we're going to represent that pulse coming from the other neuron as an X. That's the variable that is, how much pulse is coming from the previous neuron. And it's passing through a synapse. Okay, so the synapse is represented by this W, or weight. It says how much of this pulse makes it through to the next neuron. It's the strength of that that axon, the previous neuron firing, going through to the next neuron. And how does it get into the next neuron? It gets into the next neuron through dendrites. So if we multiply those two together, so our synapse is controlling how much by multiplication gets through to the dendrite. And this is when you multiply it together, this is showing going into the next neuron, the cell body. And we have multiple of those dendrites coming from different synapses, from different axons, going into the cell body. And in the cell body, it's just adding up all these inputs. Okay, that's what this summation is. It's adding them all up. This bias, don't worry about it for now. That's a mathematical construct to make sure that if all of your inputs are off, okay, you still have something coming in. This B makes it so that you don't have zero coming in. And then once you add up all of these and the bias, the B, then it goes through this function, and this is going to be the activation function, which we're going to show all of those. So we're passing this summation through, we're taking the function f of that, and then that's going to be your next output, which will become your x to the next neuron. That's the axon. So here we go. So the output, if we write what this value ends up being, it's a f of whatever's in here, which remember, this is the sum of all of those inputs. F of all of that, that's what goes into the output, which goes to the next neuron, goes to the next axon, I should say. That's an axon. All right, so really what I did, I just showed you a perceptron. Now we're going to show you that math that I just showed you in a little bit different flavor, which is more the flavor of how neurons were developed, decades ago. We have all those inputs, all the X's, and a bias. Okay, we have all the W's. We just showed all the W's. Those are weights. Those are strengths, or the synapse. Then we have the summation and the activation in the cell body, and the output being an axon. So it's really the same thing we just did, drawn a little bit differently. Here we have all the inputs. And I'm showing this over and over again so that you get into your head, what this neuron looks like mathematically. And you should be able to recognize how this looks, just like that, the biological part of it. So you have the inputs and the bias, and we have all these weights, okay, multiply by the X's, sum them all together, and then pass through an activation function. And we'll talk more about the activation function shortly. Okay, so that was converting that biological piece to the mathematical one neuron. Now let's write more math about this, a little bit more, and show how, another picture of what our neuron could look like. This is just one neuron, just like we had before. Here it's G instead of F. Okay, we have all these thetas, which are multiplied by the X's, all your inputs. And if we just write it this way, instead of the thetas, we write W's times all the X's. And then take this summation and just pass it through a function, a G. That's our activation function. If you've done any modeling at all, statistical modeling, basic, data science, machine learning, you'll recognize that this is logistic regression. So our, one neuron is exactly the same as our logistic regression equation, passing through. We have all these inputs and we have one output. The output is, again, the activation function. Here is an activation function. Okay, it's a sample one. Happens to be the most popular one, but it's only one, where we apply that activation function to the summation of all of our weighted inputs. Okay, you'll hear that a lot, weighted inputs in neural network talk. Okay, and something else about logistic regression, if you remember, your feature importance is something in linear and logistic regression is all these weights. It says how important is each one of these inputs, how much of them, when you multiply, are getting passed through. And then our logistic regression is actual activation function. Okay, so I just showed you one neuron. Let's make this more complicated. Instead of one neuron, let's have three, A1, A2, and A3. These are not neurons. Okay, if we go back with this picture, these four things are not inputs. Remember, they're just values coming in. They're values coming out of the previous layer, if we have a previous layer. But that's your input to these. And we've got three neurons instead of one. So instead of having just one neuron and then four inputs and then four weights, we now have 4 times 3 or 12 weights. So if we want to write that same function that we wrote before with a matrix, with linear algebra, if we want to write it out, we would write it like this, where see these blue lines are for the blue weights, the green lines are for the green weights, and then the orange are for the orange weights for this third one. So we take those, write it like this with a matrix, write this inputs as a matrix, and then we add that bias term, one bias for each neuron. We would get something like this, when we multiply it out. Anybody that's done any linear algebra, you know, when you multiply matrices together, it ends up looking like this. So you take this right here. This will be three values, once you add these together, and pass it through the activation function. You now have the output of the neurons. So this is the way, when you have more than one neuron, it has to be, it's going to be more complicated. The math is getting more complicated, the algebra. So you write it in linear algebra terms, matrice multiplication. And then we say this is our weight, our W. This is our X matrix. This is our bias matrix. And here, through activation, we get our output. And this is how you'd write it as a function. F of Wx plus B equals A. And then sometimes you write this as Y, because Y is an output. But in this case, we wrote it as A. Okay, so that activation function. When we talked about the biological part of this, okay, we said that the neuron turns on if it gets enough input. So what we're showing here is if we have enough input, so that's on the input. Input is along the x-axis, and the output is the y-axis. If we have enough input, then our output goes high, goes all the way on. Our input, if we don't have enough input, if we add up all of our inputs, weighted sum inputs, then we have not enough, and we have a 0 coming on the output. The neuron is not activated. And this is just the way you would write that mathematically. F of x equals 0 for anything where our input, our x is less than 0, and 1 for anything where we have enough input. And this is the binary step activation function. And something you need down the road in the next lecture, we're going to talk about how we have our neural network learn. We need to take the derivative of this activation function. So this is how the derivative would look like. Derivative is a slope for x not equal 0. We have a slope of 0 for x. When it's at 0, it's a vertical line, which means an infinite slope. So that's why we have a question mark. Don't worry about the derivative tonight. Just be aware that that's the case. All right, so another activation function is this logistic / sigmoid, which is, I showed you that here before, 1 over 1 plus e to the minus x. And that's what it ends up looking like. Your input being negative gives you a small input. And the bigger your input is, the higher, or the closer to 1 it gets. It converges onto 1. And here, right in the middle, right where x equals 0, we have a 0.5, right at half. When we take the derivative, we get this. We have no question mark. We have no vertical line here, so we can take the derivative of this curve. That's why this one's preferable to the step, actually, because of that, because we can take the derivative. Another very popular activation function, where remember the activation function is what we're passing our weighted inputs, weighted sum through. Another one is this RLU, rectified linear unit, which means that if we have a negative x, okay, negative input, then we get 0. Our neuron is not activated. If we have a positive output, then we just get whatever that is on the output. Y equals x. F of x equals x for x greater than or equal to 0, or 0 if it's less than 0. And for this, the derivative is 0 for when it's less than 0, and it's actually 1 if it's greater than or equal to 0. Greater than 0. At 0, it's undefined. And that's the problem with this one, is it doesn't have a smooth derivative. Okay, so these different activation functions are just part of how the neuron works. It's what output, it's what turns on or off the neuron. All right, so now we're going to build up our neural network. This is we went through the basis of, okay, where did the neural network come from, to what is the mathematical part of it. Now we're going to start stitching them all together, all those pieces we just built. We're going to start with the basic neuron that we started with, one neuron, okay? And this is called a 4x1 neural network, which means 4 inputs, 1 output. So one neuron with 4 inputs. And we call this a layer, okay, the inputs, even though it's not neurons, it's just a layer of inputs. And then we have our output layer. So this is one layer and one neuron. Everything that we've been showing up to now, it looks like this. So let's make it a little more complicated. Now we're going to add some neurons in the middle, okay? Originally we had an output and 3 inputs. Now we're going to stick these ones in the middle, okay? And then have our inputs feed that middle layer, okay? And our middle layer is going to feed our output. So now we have like this buffer in between. And this is called a 4x3x1 neural network. So that means 4 inputs, 3 in the hidden layer. This middle layer is called the hidden layer because the output can't see it. The input people can't see it because it's buffered, by the input or the output. So it's hidden. So how many neurons do we have? We still have 4 inputs, but now we have 3 more neurons plus the 1 output neuron. So this is 4 neurons. Basic 4 neuron, 2-layer neural network. And once you go to this level, okay, you've gone from a basic 1-layer neural network to deep learning. Okay, that's all deep learning means, is more than 1 layer. And what this means is you can represent a much more complex model with this, because what we're doing is we're taking an input and coming up with an output. So we're modeling a system, and we can model a more complex system with this. Do we need, how many arrows do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12, just like before, but we have more. Okay, these are not the output. This is the output. So we have 3 more, synapses, weights, whatever you want to call them. We have 3 more arrows. So we have a total of 15 different synapses or axons, dendrites, and the synapse in between. Okay, so now let's look at a wider network. And the application for a wider network, you get much more interesting things out of it. This is also a 2-layer neural network with, these are the inputs, and these are this is the hidden layer, and this is the output layer. So how many neurons do we have? Well, let's talk about inputs first. How many inputs do we have? The way we drew this, okay, with this dot, 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 we have 784 inputs. Why? I'll explain in a minute. How many do we have in the middle? We say 16 down here. There's this dot, dot, dot. So it's not 5. It's 5 plus whatever's here. And what we're saying is 16. That's an arbitrary number. How well this works depends on how many hidden layers. On the output, how many neurons do we have? We have 10. Okay, because we have this dot, 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 10 outputs. So what this is 784 inputs, 16 hidden layers, 10 outputs. Now, what are we going to do with this network? Okay, what if we take a 28 by 28 grid, okay, and draw numbers on it, handwritten numbers. It's a grid, it's like pixels. Everybody understands how to take a picture, that's a representative of, it's represented by pixels. We can basically tell what those handwritten numbers are. And this will be another lecture, is actually developing this with Python, developing this network and showing how you can do handwritten numbers. And this is, decades ago, 3 decades ago at least, that we were doing this level of handwriting recognition. So the way this works is we put that, we say which one of those pixels is lit up, and then we give it a number going in. All the other ones that are not lit up, give them a 0. One of these, 0 through 9, will light up depending on what is on that input, what is on those pixels. And that's how this neural network recognizes handwritten numbers. So this is just a way of looking at the count. And that data set, okay, the handwritten numbers, is a very popular data set, the MNIST data set, early image recognition, as in like, a while ago. And so that's how many arrows do we have? 784, by however many you have in the middle, 16, and then 16 by 10 on this layer. So that's how many synapses, axons, dendrites you have. How many neurons do you have? 16 plus 10 is 26. That's it. To recognize handwritten numbers, all you need is 26 neurons in exactly the same form I just presented. That's all you need, and you can do handwritten numbers. This is how the brain works. This is why we're so smart. All we need is 26 neurons, and we have 100 billion of them in our head to recognize handwriting. It's pretty amazing. That's how smart we are. All right, so let's talk about deeper neural networks. That was a very basic deep neural network. Let's go and look at deeper neural networks. So before we had just one hidden layer, okay? Now let's do more hidden layers. Okay, now we have two hidden layers. We have the input, okay? We call that layer, but it's not actual neurons. Then we have 4 neurons in this hidden layer, 4 neurons in this hidden layer, and then 1 in the output. So what's the application of this one? I don't know. Addition could be the application of this one. And we would see that we can actually do that. So this is a very simple, deeper neural network where we just added 1 neuron or 1 layer. But there's also even more than that. We could have, 100 hidden layers. Okay, and that's how convolutional networks have come about. And the neurons are a little different in just that they're different activation. That's all. All the activation we've been doing up to now is the same kind. I showed you before. Same thing as what's in logistic regression, but you do different kinds, like the ReLU. And then you can do what's convolutional neural networks do, which is better image recognition. Not just like handwritten numbers, but like faces. Okay, much more complex pictures, more pixels. There's also recurrent neural networks, okay, which is where instead of just feeding forward all the way through, you have feeding backwards or feeding across. So that's all that is. Autoencoders are where you have the same thing on the input as you do on the output. And you can do some special stuff with that. Okay, so so I just talked about these advanced neural networks, like convolutional neural networks. I'll show that structure in just a second. Recurrent neural networks, I'll show that one as well. And a very special type of recurrent neural networks is the LSTM, long short-term memory, which you can do neural networks with a combination of these. I know this is way beyond what we're talking about here. What I'm doing is just, I'm going to show you extensions of the basic neural networks. So the CNN looks like this, where you have this very complex picture at the beginning, feeding through all of these layers, all the way to the output. And very basic, just neurons throughout all of these. And you have different types of neurons, neural layers, convolution versus ReLU versus pooling. You just one after the other of all of these layers, and we end up with being able to tell whether that's a car, truck, van, or bicycle. Okay, but it's all the very basic structure, the structure I just showed you. Just add more and more and more and more of it. That's all it is. So RNN, recurrent neural network. Here's some I'll stop this in the middle here. Or I guess, oh, that's this one. I can stop this one here. So recurrent neural network, I'll just run this one. Takes the output and then puts it back to the input or puts it to the next one. And what you do with recurrent neural networks is you have a time aspect or an order aspect stored in it. Like this is great with natural language processing, because language has an order to it. You have words made up of symbols, these letters, and also then sentences made up of words in an order. So like you put each word on the input, and then you get the meaning on the output. So that's how neural networks work, how recurrent neural networks. More advanced, these are going to be more lectures that we'll be showing in the future. And then the combination between the two, like if you have your CNN structures at the beginning, and then the long short-term memory structures in the middle, and then on the output you have just like the basic structure that we started with, and the input being a picture or words, and the output being meaning. Feelings is another kind of meaning. All right. So thank you guys. I really appreciate your time. Hopefully you got a lot out of this. Thank you, Simplilearn, for putting this on. There's lots of classes that Simplilearn offers that go into this in more detail, walk you through the Python. You'll practice it. And also I'll be doing more lectures like this with more detailed subjects. Thank you and have a good one.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.